Okay, hello and welcome back, everyone. So we're moving on within this section of common rules of the derivative to the power rule, and the reason why I saved the power rule for today is that I've got this aside over here, which is on factorials and binomial coefficients. So if you've never heard of either of the two of those, or even if you have and you're a little rusty on what they actually mean, we're going to discuss them a little bit and kind of how they interact with this power rule, because a natural way of proving the power rule, or actually showing that it's true, uses binomial coefficients quite a bit. But before I get into that aside, let's just state the power rule. It's kind of everybody's favorite rule when it comes to derivatives, because it allows us to take derivatives of polynomials as long as linearity is included. And that just says that if we have a monomial, and every time we use this word monomial versus a polynomial, a monomial, Greek prefix mono meaning one, there's just one term of the form x, our variable, to a power n, where a polynomial has poly or multiple terms. So it could have something like x cubed plus 2x squared minus 3x. There are multiple terms to a polynomial. There's just one term to a monomial, but they both consider the variable to a specific power. If I look at the derivative of a monomial, power rule says, what do I have to do? I look at the power, I bring it out front. That's what gives me the n here, and then I also subtract 1 from the power. So bring power down to the front and subtract 1 from the power. That's what the power rule says. Before we get into the proof, it's time for this aside. So factorials and binomial coefficients. We'll start with factorials because we actually use them to define the binomial coefficients in a bit. The factorial of a natural number, so we're going to just look at n here, n being 1, 2, 3, 4, 5, etc. It's denoted by an exclamation point. So factorial of n is n exclamation point. And it's defined by the repeated product starting at the number that we're looking at. So starting at n and then multiplying by every number smaller than that number. So n factorial is defined by n multiplied by every natural number smaller than it. So the way I've written it here, n minus 1, n minus 2, I'm just reducing, the natural number all the way down to 2 times 1. So until I run out of natural numbers. There's this little extra caveat that we have to define the factorial of 0, because it's a useful factorial to include. We don't have factorials of negative numbers, but we do often work with the factorial of 0. So the factorial of 0 is defined to be equal to 1. And there's a few ways that you can justify that. The first one is that these factorials actually describe the total number of arrangements. So n factorial describes the number of possible arrangements of n objects in a row. These are called permutations. So n factorial is equivalent to the permutations of n objects. So the total number of permutations happens to be equal to the factorials. How many ways are there to arrange 0 objects? Well, there's exactly one way to arrange 0 objects, because the empty arrangement is the only one you can recover. So there is exactly one way. The other way that we can interpret it is that factorials have to satisfy this identity. The previous factorial, if I just end up multiplying by one larger number, since the previous factorial contained all prior multiples, all I have to do is include the very last number, and then that gives me the next factorial. If you just rearrange this definition, you see that n factorial is equal to the next one, so n plus 1 divided by n plus 1. Well, if I plug 0 in on the left-hand side, then that has to be equal to 1 factorial divided by 1, and we know that 1 factorial is 1, so 1 divided by 1 is equal to 1. So multiple ways of guaranteeing that 0 factorial is equal to 1. It just feels kind of strange. We're going to eventually counter objects that look like a division by a 0 factorial, and it feels like you're dividing by 0, but you aren't. You're actually dividing by 1, and so everything is perfectly fine. So let's look at examples of these factorials. If we just look at the 0 factorial, we already decided that was equal to 1. 1 factorial is equal to 1 multiplied by all of the natural numbers smaller than 1, and there are no natural numbers smaller than 1. 2 factorial equal to 2 times 1. 3 is 3 times 2 times 1, which happens to be 6. 4 factorial, 4 times 3 times 2 times 1 happens to be 24. 5 factorial, 5 times 4 times 3 times 2 times 1 happens to be 120. And like I said before, you can think about it like this case to that case is a multiplication by 2, and then a multiplication by 3, a multiplication by 4, multiplication by 5, and so on. So multiple ways of thinking about the factorial. These first few numbers pretty useful to memorize. 0 factorial is 1, 1 factorial is 1, 2 factorial is 2, 3 factorial being 6, 4 factorial being 24, and 5 factorial being 120. Of course, 6 factorial, you just multiply 120 by 6, you get 720. I've never had to use 7 factorial, aside from a case when I had a computer readily available and I could look it up. So kind of 6 factorial is where it stops being useful to memorize. But those are the factorials, and they allow us to define these things called the binomial coefficients. And so if you've never seen binomial coefficients before, they have a very interesting notation. Kind of looks like a fraction, but we have these parentheses around the numbers, and then we don't have a horizontal line between them. So we're stacking two numbers on top of each other, in this case n and k. We put parentheses around them, and not a fraction. If you ever speak this aloud, this kind of parentheses n over k situation, you speak it aloud as the words n choose k. And the reason it's called n choose k is that these happen to compute how many ways one can actually choose k objects from a collection of n total objects. So if I have, n different colored balls in a bag, how many ways are there of choosing k of them? Or if maybe I have 10 different colors of balls in a bag, how many ways could I choose 5 of them? That would be me evaluating 10 choose 5. So 10 balls, choose 5 of them out of a bag. How many possible combinations are there? So that's called the binomial coefficient, but you speak it aloud as n choose k, so you're going to hear me say that quite often. Now, what is it equal to? Well, it's defined by, you can actually go through it's called combinatorics. You can go through the work of analyzing a situation where you have a bag of n balls, different colors, and you want to know how many possible ways there are. Of course, that's going to be closely related to the total number of arrangements of these balls in some specific order. So that's why you see those permutations or the factorial show up right away. But because when we're choosing balls out of this bag, we don't really care the order that we choose them in. You get some terms that you have to divide by, so you don't double count. I'm not going through that work today. If you ever take a course in some places we'll call it discrete math, but combinatorics is usually the course that you look into, or even probability. You do actually go through the work of deriving this formula. But for now, we just think about the formula as, well, the n comes straight across as n factorial, and then the k comes straight across as k factorial as well. So you really do have this ratio of n factorial to k factorial, but there's this extra term n minus k factorial in the denominator, which does account for that double counting that would happen if you cared about the order that you extract things in. But really, I just like to think about it as the sum of both the numerator and the denominator, sum of terms in factorials adds to n in both cases. So in my mind, I always remember that the n and the k both come straight over as an n factorial and a k factorial, but in the denominator, I want both the numerator and the denominator, the total sum of the terms in the factorials, to add to n. So that's where I have to account for that n minus k, because n minus k plus k, and since I have those both in the denominator, adds to n. Otherwise, just memorize it for what it is, and actually there's going to be one other way that we'll establish how to compute these binomial coefficients. So if I look at examples of these binomial coefficients, what do some of them look like? Well, 0 choose 0, pretty classic example. You just have 0 factorial, which we know is 1, 0 factorial is 1, 0 minus 0 happens to be 0, factorial is 1, so you just have a whole bunch of 1s divided by one another. That's of course going to be equal to 1. 1 choose 0 is a 1 factorial in the numerator, still equal to 1, 0 factorial still equal to 1, 1 minus 0 factorial still equal to 1, still a whole bunch of 1s. You have 1 choose 1, that's going to be a 1 in the numerator, 1 in the denominator, and a 1 minus 1, which is 0 factorial in the denominator, still a whole bunch of 1s. So there are really a lot of 1s sitting around here. Thinking back to colored balls in a bag, how many ways are there of choosing one ball out of a bag with one ball in it? Well, there's exactly one way. Or if the bag has 0 balls in it, how many ways are there of choosing 0 balls out of the bag? There's only one way of doing it. So you're going to see a lot of 1s show up. We start to see them all the way down this diagonal and actually all the way down this vertical term too. But let's look at some maybe more complicated cases. If we look at 4 choose 2, for example, calculate 4 factorial. Let's recall that that's actually 24. We calculate 2 factorial over here. That happens to just be 2 times 4 minus 2 factorial, which happens to also be, 2 factorial, which happens to be 2. So 24 divided by 2 times 2, 24 divided by 4, and we get 6 out of that. So if you went ahead and actually computed all these factorials and simplified, you would get all of the numbers which I have on the screen here. Now what's actually important is this next line. I say notably, if we rearrange the red numbers into a symmetric triangle. So what I'm going to do, I'm going to take all these numbers that are vertical and I'm going to kind of bow them out to the left, since I've already got these diagonal ones. So I'm going to make everything symmetric. And what I end up with is the following picture. Here I've got 1, 1, 1, 1, 1. Those are my vertical terms. And then I have 1, 1, 1, 1, 1. Those were the original diagonal terms. And then what happens in the middle, if I align all the rest of the numbers correctly, let's just verify that I have over here a 2, and then I have 2 3s, and then I have a 4 6 4. Going back over here, there was a 2 2 3s, and a 4 a 6 and a 4. If you've ever learned about Pascal's triangle, that's exactly what we've constructed here. So Pascal's triangle really is this triangle. You can think about there being infinitely many zeros out to either side if you want. But if you include these infinitely many zeros, what's going on in Pascal's triangle is we start with the 0th row up here, because that was corresponding to, recall my 0 choose 0 situation. So we've got the 0th row choose there. And then to find the next row, we just add the two numbers above a specific spot in the previous row. So these two zeros are going to just add together to give me another 0, but a 1 and a 0 add to give me a 1, a 1 and a 0 add to give me a 1, and then I can repeat the process from there. So if I add my two 1s together, I get a 2. If I add the 1 and the 2 together, I get a 3. Same in the other side. If I add my 3s together, I actually end up with a 6 in the middle. If I add my 3 and my 1 together, I end up with a 4. My 3 and my 1 together, I end up with a 4. And so we could continue this as far as we want, and this ends up, creating the binomial, the rows of the binomial coefficients. And so that's what's really nice here. So in that sense, if I wanted to maybe find the fifth row, right, 5, choose k for, every situation of k, 0, 1, 2, 3, 4, 5. If I want to find the fifth row, put a 0 there, put a 0 there, add them together, 0 and 1 makes a 1 and a 4 makes a 5, a 4 and a 6 makes a 10, a 6 and a 4 makes a 10, a 4 and a 1 makes a 5, and a 1 and a 0 makes a 1. And if you would go through the work, even with the definition of the binomial coefficients, you see the same numbers pop up, right? So if I wanted to choose something like 5, choose 3, for example, my numerator 5 factorial happens to be 120, but we'll get there soon. 3 factorial over 5 minus 3 factorial. So ends up being 120 divided by, 3 factorial is 6. 5 minus 3 happens to be 2, whose factorial is 2. So I have 120 divided by 12. I have 10, and there is my 10, which exactly corresponds to 5, choose 3. So this Pascal's triangle is kind of a shortcut method of producing the binomial coefficients if we don't like going through all this work with the factorials. So what's the real point? Why am I introducing this here when I'm dealing with the power rule for derivatives? It's because of this theorem called the binomial theorem, which we'll end up using. Well, we use it to prove the power rule, but we also use it quite a few other times in this course. It's really, really an efficient theorem for us to keep in mind, really the rest of our mathematical careers. And what this theorem talks about is it is an efficient way to expand binomials. And what is a binomial? Well, this goes back to me saying monomial and polynomial from earlier. A binomial is, a polynomial of exactly two terms added together. So we've got x plus y there, but they're taken to a new power. So a binomial is x plus y to the nth power. What does the binomial theorem say? Well, it says if I want to expand x plus y to the nth power, I can do it using these special terms, these ideas of the binomial coefficients. And of course, that's where the name comes from, binomial coefficient, is that these are in fact the coefficients of a binomial expansion. So where do these coefficients come from, or how do I find them for a specific binomial? So there's my specific binomial. I've got an x, and I've got a y, and I've got a power n. What am I going to do to expand according to binomial theorem? Well, I'm going to take my n. I'm going to include it in the top of every binomial. So every single binomial coefficient in this expansion has an n in it. And then what else does the theorem say? Well, it says that the total power on each x to the n minus k, y to the k term is n, right? If I add the powers together, it's always n. So n and 0 add together to give me n minus 1 and 1 add together to give me n minus 2 and 2 add to give me n, 2 and n minus 2 add to give me n, 1 and n minus 1 add to give me n, and 0 and n add to give me n. And then even better than that, where do these kind of the bottom of the binomial coefficient terms come from? Well, they just come from, they're exactly the same as the power on y. So the power on y is also in the bottom here. So power on y is in bottom of binomial coefficient. Or in other words, you can say, well, how does the power on y work? Well, it starts at 0, and then it just increases 0, 1, 2, 3, 4, 5, blah, 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 up to n minus 2, up to n minus 1, up to n. And then the same thing happens in the bottom of binomial. 0, 1, 2, 3, 4, all the way up to n minus 2, n minus 1, and n. So this is a very abstract the way I've written it. To actually show you what it looks like is a little bit more straightforward than that. So let's go to the example, which is using binomial coefficients for a quick expansion. Suppose I wanted to quickly expand something like x plus 1 to the 4th power. Well, what I do is in my head, or I had these memorized because it really doesn't take me long to memorize it. I've got the Pascal's triangle in the back of my head, 1, 3, 3, 1, 1, 4, 6, 4, 1, my Pascal's triangle. And what do I do? Well, I look at the 4 in the power here, and keep in mind the triangle, this is the 0th row. It's a little bit annoying to start at 0, but as I always say, 0 is the first number. So you start at the 0th row, which really means, if it's hard to remember which row you have, just look at that second entry in the row, and that's going to be the correct number for the power here. So 4th row is actually the one sitting at the bottom here. 1, 4, 6, 4, 1. These are the binomial coefficients corresponding to 4. And if I want to expand something like x plus 1 to the 4th power, I just write out my coefficients, 1, 4, 6, 4, 1. And then I have my two terms, x and 1, that were originally inside the binomial. And every term here is given an x, and it's given a 1. And then I need the total power of these two terms to add to 4, to add to this total power of 4. Now, the way I have to do this is a little special. I just look at my first term and I start it at 4, and then I drop that to 3, to 2, to 1, to 0, and I do the opposite with the second term. I start the second term at 0, and I move upwards to 1, to 2, to 3, and to 4. And so you get these coefficients, 1, 4, 6, 4, 1 from Pascal's triangle. You get the powers 4, 3, 2, 1, 0, and 1, or 0, 1, 2, 3, 4. And then you kind of just simplify, and we end up that our expansion, x plus 1 to the 4th power is x to the 4th plus 4x cubed plus 6x squared plus 4x plus 1. So just a shortcut. You could go ahead and FOIL it all out. It's really quite tedious to go through the work of foiling when you can just get away with this lovely Pascal's triangle or binomial coefficients expansion. And to really express how useful this is, let's look at the next example. Something like 2x minus 3 to the 5th power would be horrendous to FOIL. There's absolutely no way you couldn't pay me to FOIL something like that. And so instead, what I'm thinking in my head is I'm going to that 5th row of Pascal's triangle, which is 1, 5, 10, 10, 5, 1. And you can go back to the book and verify that, or you can just reconstruct it in your head. And I know it's the 5th row, so I have 1, 5, 10, 10, 5, 1 as my coefficients. And then I go ahead and look, and I say, oh, the first term is 2x, so I've got 2x to the 5th, 2x to the 4th, 2x cubed, 2x squared, 2x to the 1st, and 2x to the 0th power. And then my second term is really a minus 3, right? So I have minus 3 to the 0, minus 3 to the 1, minus 3 squared, minus 3 cubed, minus 3 to the 4th, and minus 3 to the 5th. And at this stage, it's probably to my advantage to use a calculator to simplify some of these terms, but if you only have a dumb calculator, not a smart calculator, this will get you there, and you end up with 32x to the 5th, minus 240x to the 4th, plus 720x cubed, minus 1080x squared, plus 810x, minus 243. And so it is really quite powerful compared to having to go through the work of foiling. And we see in this case as well, a plus b cubed, the third row of Pascal's 1, 3, 3, 1, and we just step up. Well, we step down in a is a cubed, a squared, a to the first, a to the 0, and we step up in b is b0, b to the 1, b squared, and b cubed, and then simplify. It gets quite common to memorize this whole 1, 3, 3, 1 situation for cubes, because they do show up periodically. And in fact, if I jump all the way back to the beginning of this chapter, right, we went through the work of calculating the derivative of x cubed minus 2x squared by hand, and we went through this work of actually foiling x plus epsilon cubed. Well, now that we have our binomial theorem at our disposal, we see in our expansion this whole 1, 3, 3, 1 ratio show up, 1, 3, 3, 1 expansion show up. And so we could have saved ourselves a little bit of time if we had known the binomial theorem back at the beginning of this chapter. I do want to mention that sometimes we do this in reverse. So it may not be uncommon to see terms of this form where we actually kind of see a 1, a 3, and a 1 show up with kind of decreasing powers on x, 3, 2, 1, 0. And we should tell ourselves that this really is the reverse of the binomial expansion. If we wanted to simplify this, we could, and simplify it to x minus 1 cubed. Now, this tends to only be relevant in situations where maybe this was originally divided by x minus 1, and you don't want to go through the polynomial long division here. I mean, everybody hates polynomial long division. So instead of going through the polynomial long division, you recognize that the numerator can be kind of condensed into that x minus 3 cubed by kind of the reverse direction of the binomial theorem. And then we've got x minus 1 cubed over x minus 1, and the 3 would cancel and turn into a 2. And so this is just x minus 1 squared, or at that point, if you wanted to expand that out, x squared minus 2x plus 1. And so this does save you a bit of time in some division, cancellation, simplification situations if you can recognize kind of the inverse direction. But that's really getting these Pascal's triangles rows memorized. 1, 3, 3, 1, super common. 1, 4, 6, 4, 1, super common. 1, 2, 1, of course, very common. That's just the natural kind of squares situation. When you have 2 minus y squared, it ends up being 4 minus 4y plus y squared. So that tends to be something that can be useful. And I've done this entire aside, so we're finally done with our aside. And the point of this was we can actually prove the power rule for derivatives. So my guess is in your Calc 1 class, it was either proven really quickly or the proof wasn't even covered, because you do have to introduce this binomial theorem to get a proof of the power rule for derivatives. This still only actually works for natural number powers, but it's good enough for me to do this for natural number powers. For fractional powers, you have to get a little bit more clever. But yeah, let's go ahead and prove the power rule for derivatives. What we're going to do is we're going to take a derivative of a monomial. But by definition, what does the derivative say? Well, it says I have to take this monomial and I have to evaluate it at x plus epsilon, and then subtract the monomial itself and divide everything by epsilon. Well, when we just give ourselves this natural number n, and we don't really know what the natural number might be equal to expand that term or to simplify the term x plus epsilon to the nth power, we don't have a choice except to use this binomial expansion. So what I've done here is I've directly replaced the binomial expansion in And I've just written it now, right, as n choose 0, and then x to the nth power, epsilon to 0, n choose 1, x to n minus 1, epsilon to the 1, and all the way out with the rest of the binomial theorem. And the nice thing that happens here is that we have an epsilon here. We don't have an epsilon in that term, but the rest of these terms all do have epsilons on them, so we can cancel those epsilons. What's going to happen to this very first term, n choose 0, x to the n, epsilon to 0? Well, n choose 0 is really the first entry in Pascal's triangle. The far left entry, this is always equal to 1. So this is really ending up as 1, x to the n, and then epsilon to the 0 is another case of 1. So we have an x to the n here, and that's going to exactly cancel with this x to the n at the end. So those terms fall out, and everything else actually has an epsilon in it for us once we have this expansion. And so we go through the work of canceling, well, first the x to the n's, and then second all these epsilons, so they all cancel, and we get an n minus 2 there and an n minus 1 there on the rest of the terms. And what we end up seeing is this first term, because the first term arose from n choose 1. So let's see what n choose 1 is equal to. Well, that's n factorial divided by 1 factorial n minus 1 factorial. Well, 1 factorial is just 1, so this is n factorial divided by n minus 1 factorial. Well, n factorial is n times n minus 1 times n minus 2 dot dot dot. And n minus 1 factorial is n minus 1 times n minus 2 times dot dot dot. And well, the n minus 2's cancel, the n minus 1's cancel, everything cancels in the denominator. You're just left with the one copy of n in the numerator. So actually this term simplifies to n very quickly, and so it comes along for the ride just as multiplication by n. And so the only term that kind of survives the cancellation is the term n x to the n minus 1. That's your very first non-trivial entry in the binomial expansion. And then everything else becomes 0 because it's got an epsilon inside of it, and you just let epsilon go to 0, and then you're just left with what the power rule tells you should be left with, right? This is all back and equal to d dx of x to nth power, and that is your power rule. So if you've never seen that before, it's pretty fun to see. We do also have the quotient rule, but I've waited until now to actually compute it because it's the easiest way to prove the quotient rule. I mean, there's a few different directions, but my favorite way of proving it, we've already seen the product rule, we've already seen the chain rule, and actually now we've seen the power rule. So by interpreting the quotient of two functions really as a product of the numerator times the denominator to the -1 power, we can end up using the product rule because there's a product, the power rule because there's a power, and then the chain rule because we've kind of got these extra parentheses sitting around before we take the power. So there's three rules going on. It's a mixture of product, chain, and power. But if you go through the work of actually computing the derivative of this particular product, which is the same thing as the quotient, you just use those three rules on it, and what you end up with is exactly the quotient rule right here. But let's go back to the statement in the proposition, and I'll say the way that I like to remember it in my mind. So if I take the derivative of a quotient, I take bottom d top, that's how I tell myself, so bottom d top minus top d bottom all over the bottom squared. So you'll hear me say that a lot if we happen to encounter a quotient rule, say bottom d top minus top d bottom all divided by bottom squared. If I want to look at an example of the quotient rule, what do I have here? I've got x squared minus 2 divided by 2x plus 3. What's it going to be? Well, there's the bottom, and then we'll take the derivative of the top, which is the derivative of x squared minus 2. That ends up being 2x minus top times the derivative of the bottom. What's the derivative of 2x plus 3? Well, the derivative of 2x plus 3 is just 2, all divided by the bottom squared. So then I square the bottom. And I'm left with this. Honestly, you could probably just leave your answer like that if you wanted to. Don't simplify if you don't need to, but this does simplify just a tiny little bit. You can combine a couple terms together. You get 2x squared plus 6x plus 4 in the numerator, and 2x plus 3 all squared in the denominator. So there are two remaining common rules for the derivative of specific functions. These are going to be the exponential and logarithmic rules. So first one, the exponential rule of derivatives. You probably haven't seen it written like this before. I gave myself an arbitrary base on the exponential, so just the base a to the x power, rather than e to the x power, which really is the common one that we'll see this entire semester. So the derivative of e to the x power is itself. It's kind of a very special function that's left unchanged by the derivative. But if you decide to take the derivative of any exponential with a different base, the price you pay for that is just a multiplication by the logarithm, the natural logarithm of that base. This directly falls out of the definition of the natural logarithm, as you can actually write a to any power as e to that power to x, right, or e to that power times x. Now we've already seen actually the proof of Euler's number exponential show up, because when you write out the limit quotient for the definition of the derivative, you end up with kind of this limit that you want to compute as epsilon goes to 0. And one of the definitions of Euler's number e is that limit has to be equal to 1, and so you're just left with the term which factors out, which is e to the x. So we can compute the derivatives of sine and cosine using kind of these imaginary and real parts of the complex exponential. I mean, that's one of the many reasons that I've introduced that complex exponential to all of you. Because at this point, we just have derivatives on these exponentials. Because of linearity of the derivative, we just go ahead and compute the derivatives on those exponentials, and that'll give us sine or cosine. Let me go down to the proof here. If I take the derivative of these exponentials, well, the chain rule says that this I is going to come out front and this minus I is going to come out front. And then if I go through a little bit of work to cancel the i's in the numerator and the denominator, what I end up with is exactly cosine. I mean, things just turn around into that complex definition of the cosine function. And then the same is true for cosine, where the I is going to come down here because of the chain rule. And then the negative I comes down on the second term because of the chain rule. And if I simplify a little bit, I do have to multiply the numerator and denominator by negative I to simplify things the right way. But what I end up with is exactly negative sine of x. And I think that's a very nice way of seeing the derivatives of cosine and sine be what they are, which happens to be that the derivative of sine is cosine and the derivative of cosine is negative sine. You can also take the derivatives of tangent, cosecant, secant, and cotangent. These is a direct result of applying our previous rules onto sine and cosine, because the rest of these functions can be written in terms of sine and cosine. So for tangent, we're going to use the quotient rule on sine over cosine, which you'll recall I like to say is bottom d top minus top d bottom all over the bottom squared. If I calculate those out, well, the derivative of sine is just cosine, so I've got 2 copies of cosine here. Derivative of cosine is negative sine, so I've got 2 copies of sine here. Cosine squared plus sine squared. This is kind of the one trig identity I really need you to memorize. This is always equal to 1. That's called the Pythagorean identity. And because that's always equal to 1, we just end up with 1 over cosine squared, also known as secant squared for tangent. Derivative of cosecant is just by definition 1 divided by the derivative of sine. And we can think about that as, sine to the negative 1 power, different than sine inverse, right? And then I put the negative 1 outside of parentheses for a reason here. Be careful, they're not the same thing. Negative 1 outside of sine, we just have a reciprocal. And so the derivative here, the power rule is going to grab that negative 1. It's going to pull it out front. And it's going to drop the power down to negative 2. But the chain rule says, yeah, I keep the inside the same, but I also have to multiply by the derivative of the inside, which happens to be cosine in this case. Simplify everything a little bit. You end up with negative cosecant x, cotangent x. Other ways to simplify it as well, but that's the one that most people use. Similar idea for the derivative of the secant function. It's going to be 1 divided by cosine. We're going to apply the same sort of chain rule and power rule to it. And we just recover secant times tangent. And then the same sort of thing for cotangent, except now I've got a cosine in the numerator, sine in the denominator. I still have the quotient rule of bottom, d top minus top, d bottom over bottom squared. And I go ahead and simplify things here. I have negative sine squared minus cosine squared. This is still the Pythagorean identity, but really it's the negative Pythagorean identity. It's minus Pythagorean identity, and so we'll get a minus 1 or negative cosecant squared for the derivative of cotangent. Moving onwards, we do have to cover the logarithm rule, because all the previous ones were really kind of fancy versions of the exponential rule. The logarithm rule says, well, if my log has a base on it, right, a log of base a, actually ends up being 1 divided by the natural log of the number a times x. So in some ways you can think about it, well, when this is an e, it's the natural log of e, so that just turns into a 1, and you get 1 over x. It's kind of the price you're paying for changing the base is dividing by the natural log of that number. And you can see at the bottom here that this is exactly, the derivative of the natural log is just 1 over x. And primarily we do just work with the exponential base e and the natural logarithm in calculus because they are kind of the most straightforward cases. I'm not going to go through the proof of this one. We kind of already did at the beginning of this chapter. It just relies on that same notion that this is your continuously compounded interest version of e. So that limit turns into e to the 1 over x, and then everything cancels and you get 1 over x. And, the log a in the denominator comes for free once you recognize this log rule, which says that the log base a of x is natural log of x divided by natural log of a. Okay, so let's look at an example of the logarithm rule for derivatives. Classic case, if I want to do the derivative of log base 10, that's going to be 1 over log 10 times x, or the derivative of log base 2, 1 over log 2 times x. Okay, now maybe my favorite rule, and one that isn't actually taught too often in Calculus 1, is the derivative of an inverse function. So suppose for some strange reason, I'm given an inverse function, but I'm not really told what it looks like in terms of polynomials or other derivatives that I know how to compute. So suppose I can compute, the derivative of the forward function, but don't know the derivative of the inverse. That's really what's happening here, and I will provide an example that will feel very natural as to a situation of this happening. So suppose you know how to take kind of the derivative of the regular forward function, but not its inverse. There is a rule that tells us we can truly find the derivative of the inverse from the derivative of the forward function. And what happens is it says the derivative of the inverse is equal to 1 divided by, well, the derivative of the forward evaluated on the inverse. So I'm going to take 1 divided by the derivative of the forward function, but then I evaluate or compose, however you want to think about it, evaluate it on the inverse function. So a very cool little rule that we can use here to find the derivative of inverse functions. And the proof is fairly straightforward. You actually apply the chain rule to the definition of the inverse function, right? Because the inverse function is defined to cancel the regular function. You have to end up with x. Well, we know the derivative of x is equal to 1, and we know that we can compute the chain rule on the left-hand side. And computing the chain rule on the left-hand side, well, we got the derivative of the outside, keep the inside the same, multiply by the derivative of the inside. It turns out this is exactly what we want. This is the term we want. We want to find. So divide by everything else. I can spell else, and we get that the derivative of the inverse is, the 1 on the right-hand side divided by everything else, which ends up being the derivative of the forward function evaluated on the inverse. So pretty cool to see. There are some cases, I've got this example here, a second proof of the derivative of the logarithm. So you can use this inverse because the logarithm is the inverse of the exponential. You just plug this formula in. You consider the log as f inverse, where f happens to be the exponential. And well, we know the derivative of the exponential is itself, and then you evaluate on the log. So it is 1 divided by the exponential of the log. Well, those cancel, you 1 divided by x. But maybe the more important cases of this inverse rule, so let's go back to the inverse rule. This inverse rule being useful is for inverse trig derivatives. These are kind of the important ones that we care about for the inverse rule of derivatives. So inverse trig derivatives, let's see what those look like. Derivatives of inverse trigonometric functions. Let's start with sine. So sine inverse, how could I compute that? Well, I'm going to take, my rule says it's 1 divided by the derivative of the forward function. The derivative of sine is cosine, and then we evaluate it on the inverse function. So cosine of sine inverse. And we could leave it like this. This is kind of valid. Valid, but not useful. If we actually go back to our trigonometry section, we can compute cosine of sine inverse of x, actually in terms of a polynomial. So let's go ahead and do that. How can we compute cosine of sine inverse? Well, we recall that sine inverse has to be the theta value, or the angle value of the right point on the unit circle of y value y, and cosine happens to be the x value of the point whose counterclockwise angle is theta. So we're really just asking, okay, we're going to look at the right point on the unit circle of some specific y value, and then we're actually going to look at its x value. So that would be sine of cosine, or cosine of sine inverse of x. Well, this is the first quadrant of my unit circle. I'm going to write that x is equal to sine of theta here, which is equivalently that theta is equal to sine inverse of x. Well, how do I find the remaining side of the triangle? I just use the Pythagorean theorem, which says, well, the hypotenuse is always 1 on the unit circle. I know my first side length happens to be x. What is my third side length? Well, it's 1 minus x squared, and then you take the square root of that. So you find out that cosine of sine inverse of x is a root 1 minus x squared. And that actually gives you the derivative in a kind of a prettier fashion. The derivative of sine inverse of x is 1 divided by root 1 minus x squared. So either one's fine. I mean, this cosine of sine inverse of x is totally fine, but writing it as 1 over root 1 minus x squared is definitely prettier. You do the same exact thing with cosine inverse. You end up with actually the same exact answer, except for a negative sign popping out front. So we don't really worry too much about that one. I will go through tangent inverse here as well. So if I want to find the derivative of tangent inverse, what am I going to do? Well, the inverse formula says it's 1 divided by the derivative of the forward function. And the derivative of tangent, we already calculated with secant squared. You evaluate the forward on the inverse function. So secant squared of tangent inverse. But of course, since I have 1 divided by secant squared itself is 1 divided by cosine. So I have two reciprocals. The reciprocals cancel. I just have cosine squared of tangent inverse. We're going to play the same game here, but I actually won't draw this one out because we're going to think about it in our minds a little better. Tangent inverse of y over x has to be the theta value of the right point on the unit circle of whatever coordinate y over x is, and then cosine of that will just be the x value. So what I'm asking for when I say something like cosine of tan inverse of x, this is really cosine of tan inverse of some y star and x star, where this y star over x star equals my original point here, x. So how do I find that point? Well, I can rearrange x equals y star over x star to say x times x star equals y star, and then since I know that the point x star y star is on the unit circle, well, the definition of the unit circle is that the x value squared plus y value squared is equal to 1. So actually I have two equations and two unknowns here. If I go through solving that system of equations, we find out that x has to be equal to, or really x star has to be equal to root 1 over 1 plus x squared. So that means the cosine of tangent inverse of x is root 1 over 1 plus x squared. But we weren't talking about cosine of tan inverse, we're talking about cosine squared of tan inverse. So I'm going to take the square of that entire square root, which is just going to give me 1 over 1 plus x squared. So you find out that the derivative of tan inverse of x is 1 over 1 plus x squared. Kind of realize I went through that one really quick. I would suggest you look at the book for actually all of these situations of the inverse functions, because they do get a little bit tricky. I did a good job describing my intuition for actually computing them, but just in the video I don't think it's going to be able to come across quite as easily. So I would open up the book and just look more concretely at those. That's going to be all I have for this video. I just want to finish and let you know that there's this table of all of the derivative rules kind of succinctly written here, so you can refer to them whenever you want to, rather than having to refer to every proposition we just covered in the last 2 days. So that's all I've got for today. Bit of a long one, sorry, but thanks for hanging in there. I'll see you in the next one where we talk about integrals. Bye.